Okay, good afternoon. My name is Zheng, and I hope you feel happier now looking at the clock I have. It's actually already Saturday. Hope you had a good week. So I'm going to talk about QEMU's event loop today. So this is what I will cover today. The first half is about the event loops in QEMU we currently have. I will give an introduction about how it works and what are there. And from there, we can see a few challenges we are facing now, including a few aspects such as consistency and scalability and correctness. And I will show you what the real challenges mean and what can we do to fix them. So QEMU is an event-based program. That basically means you have a loop that dispatches events. And for now, we have several. We started from the main loop, which dispatches file descriptor events. And later, we added more threads into the program. vCPU were added when KVM is enabled, and it's responsible for running the guest code. And this thread also dispatches port I/O events and memory I/O events. The third one, iothread, is recently added for the purpose of enabling multi-core performance of host. And it is responsible for running the dataplane code. So both the main loop and the iothread loop are event loops. They all work on some file descriptors and dispatches the event in a way that has a lot of common. So let's look at what is a main loop. What it does is to dispatch file descriptor events and a few non-file descriptor services. The file descriptors include 4 parts. One is the AIO, which is the block layer read, write, and also the I/O event FD, which is used in the virtio multi-queue. The second one, I/O handler. This is a legacy file descriptor handler interface we have inside QEMU. And it still works with net subsystem and an NBD server and audio subsystem and UI, VFIO, and extra. The first AIO and the second I/O handler has quite a few things in common because they all watches for events for certain file descriptor sets with a similar interface. The third one is a bit different because it also belongs to the net subsystem, but it's particularly used in user space network emulation. It's called Slurp. It's a library inside QEMU, but it's very specially hooked into the main loop, as we will see later. The fourth one is the character devices. It works as very simply as the AIO one because they are both glib G sources. That's about the file descriptor events. And we have timers and bottom halves. These are 2 special APIs for internal use of the QEMU various subsystems. So with all these elements, this is the event loop. Only 3 steps, which is simple. The first one is a preparation. It's also the entry point. So in this phase, you do all this last-minute preparation of various events and data structure once you are prepared, you can do the pull. The pull basically watches for new events from the kernel so that whenever any I/O happens, you get notified, and you go on with the event loop into dispatch step. In the dispatch step, you will dispatch by calling into different callback functions that's registered by various subsystems. So let's get a little bit more details by listing what is actually there in each step. So the first one is preparation. To prepare, we need to fill in an array of file descriptors, which is useful to be passed into the second one. So that is what basically slurp and IO handler and glib pull does. The other thing they do is timeout. Timeout is interesting because it's also passed into the pull function in the second phase. We do not want to block forever if we do not get any new file descriptor events, because we also want to emulate timers. So the timeout is basically most importantly for timers. And you can see in the first prepare phase, we also have a calculation for timeout of the main loop timers. So when we do the poll, we will get a list of events from the system. Each event means there are some data activity happening here, and we should dispatch the event. So the dispatch basically call into each subsystem, and each subsystem will take care of calling the upper level users. By users, I mean the calling code of each. For example, in slurp code, the dispatch would be reading or writing the slurp packets. So that last step is to dispatch all the timers. All the timers are maintained in a list, and this function will work through the list of timers and see which timers in that has expired. So let's compare it with iothread. Iothread is simpler. It has a loop that looks very short. AIO pull is an interface of the AIO part that we just mentioned. So it does basically the same set of actions, except for the prepare, pull, check, dispatch are all wrapped in AIO pull. So we very quickly realized that the two do the same thing. Okay, so I'll directly go into what challenges are there. Challenge one, as I mentioned, is a consistency. The iothread does things in a similar fashion as the main loop. As an interface, the AIO is basically what is only available in an iothread. But the main loop has a few more things that we don't care in iothread. But that's something in common. And the set of file descriptors we have in iothread a special builder of the array. And when we are in main loop, we have this glib API to query that all those functions that are all those functions of handler that added to the main context. And there are also some synchronization semantics that shares basically the same idea. And the last line is GSOS support. The main loop supports GSOS so that it can be used by character devices, but with iothread, we are not very compatible with that interface. So it seems that some things are in common and some things are not. But why should we care? Why should we convert them? There are mostly three reasons I can think of. The first one is because main loop is a hacky mixture of different stuff you just say, because all those different specific functions are hard-coded inside the main loop. But that's not quite important, because it's already working. The second good reason is to reduce the code duplication between IO handler and AIO, because they share exactly the same interface to support the different subsystems, like device emulation and things like that to use. They used to be different in a small area, where IO handler has a more complicated FD pool stuff that is basically a special preparation. But I already removed that. So what we can do is go further and convert them. So the last reason is better performance and scalability, which is what I'd like to mention more here. So for that, we strictly go to the second challenge, scalability. Because as we know, the main loop is hooked up by a few functions that manages each custom list of file descriptors to read. It's a complicated algorithm compared to what we would have when we converge them. Once we have multi-queue, we will have some more descriptors, like those used in IRQFD and as the IO event FD. Once we open more disks and attach to the guest, we will have more image FDs. All this add to the slowness of the main loop because of following reasons. One is the pool FDs fill needs to work through all those list of FDs to fill in the array that we would pass into the p-pool. And the QEMU pool NS itself, which basically is a wrapper of system called p-pool, it takes longer because of the inheritance of the call. The reason is that we pass in an array that has a very big length. And the kernel also needs to work through a lengthy array. Also, after we do the pooling, the dispatch working through them will take more time. So, as we can guess, if we add more disks to a virtual machine, we can see worse performance. From the left, the purple bar is read, the green bar is write, and the blue one is random read-write. If we have only a few descriptors, it's okay. We can have a fairly good performance. The data is it's very close to 20,000 on my testing with a ramdisk. And if we go to the higher number of SCSI disks that attached to the same bus, which basically means we have more file descriptors inside the main loop, we will have worse performance. The trend is mostly linear, so it's a problem. And now we have an iothread that can move some of the file descriptors into. For example, if we enable dataplane on virtual block, we can have that set of file descriptors moved to separate threads. So we don't have a large set of file descriptors to query for in a single event loop. That may be better, but it's still not ideal. That is because even though we can have separate threads, we cannot have infinite ones. We want to limit the number of threads because we don't have so many resources to run all this, especially with virtio-scsi. Virtio-scsi runs as one single device model. It doesn't have the ability to scale across iothreads. Even if we now enable the multi-queue, we don't have multi-thread support for multi-queue. So that still is a problem. So that basically means now we have ON performance. So the solution is to use the Linux native syscall epoll because it scales well to a large number of watched FDs. That is what the man page says, at least. The interface is like this. Firstly, you create an epoll FD with the epoll create function. And then you control, add, or modify or delete file descriptors you want to watch into this file in epoll FD. And when you are ready, you call the epoll wait function, which is basically the replacement for people. And this function will wait for the new event to arrive for you, just as the people does. But unfortunately, this doesn't fit in the current main loop model because the main loop is a hacky mixture of various stuff. But good news is that AIO interface is very similar. In AIO, you create an AIO context, and you call AIO set FD handler to add or remove file descriptors to this AIO context. So that's what we can do. We can convert the AIO version API to make it use the epoll system. Okay, so here's the idea of the new implementation. In the AIO set FD handler, where you insert this interesting FD into your watched set of FDs, you can just call the epoll control to update the pool FD. And in your AIO pool interface, you can just call epoll wait. The idea is pretty simple, and it's a low-hanging fruit. I've already done this and sent the patches to QEMU upstream list, which basically shows quite promising results. Now these three charts are comparing read-write and random read-write on iothread. So it has to be a virtio-scsi iothread because we don't have multiple disks on the virtio block one. And this is easier because I don't need to create multiple devices to handle multiple disks. I only need to attach a SCSI disk to a single bus. But the case for virtio block data plane would be the same. We can see that the improvements are pretty significant. Okay, but there is another problem introduced by this. The epoll wait function is not quite on par about the timeout of the people because the granularity, the precision is lower. It only supports a millisecond. And in people, you can have a time spec which has nanosecond. That's important. We don't want to just rounding that timeout to adapt to this epoll wait because that would hurt the timers. The timers need a precise timeout and dispatch. So it can be worked around. without introducing a brand new epoll wait 2 syscall. That's a simple approach as well by using the timer FD. Well, it's a well-known interface. I won't go into explain it, but we can add a timer FD into the epoll FD so that for each epoll wait, whenever the timer FD has fired, we will see the return so that we don't need to do anything about the timer FD, the timeout of epoll wait. But from the previous results, where I converted things in the dataplane iothread, we don't need this yet because we don't have any timers inside the dataplane thread. Everything is attached to the main loop. So this is for future. If we want to move epoll into main loop as well, and we will see it now. So the main loop has more stuff there. How can we make use of epoll? Basically, we can't with the right code, but we can change it. We can move the IO, other things on top of AIO. We can move the IO handler, we can move the slurp, and also the GSOS. We just need to make AIO interface more powerful. So now the mission is assigned. We need to resolve the challenge number 1 so that they are the same, and we can use AIO interface in main loop, and we get the epoll performance. So these are concrete steps. 1 is to make the IO handler interface consistent with the AIO interface. As I said, they used to be different, and it's hard to port IO handler onto AIO. Now they are the same, and we can make the conversion. Other than IO handler, we have slurp, and we have slurp is also a hack. We don't like that, so we can try to change it. There are patches posted, but I failed to make it into 2.4.
I just wanted to point out that there is now a maintainer for slurp.
Yeah, I was just saying that.
Sacrifice themselves. I don't know.
So let's just make this into 2.5 with everything, every good things else together. And after that, we can look into the character devices. They are special because they use basically a special GSOS and actual working GIO interface. But that's doable with a slight change in the API and maybe introducing more stuff that supports the preparation they need to have. This is to be done. So hopefully, we can eventually put this stuff into this chip so that everything else run on top of AIO. And AIO is used by main loop so that the main loop has a better performance. This also means that the main loop doesn't have to do its own steps of the whole event loop. It just calls the AIO pool like in the iothread. So the difference in the bottom is that if we only convert things on top of AIO, we would still need people. But later, when we just eliminate everything in main loop, we can have the epoll. Okay, that's about it. I'll go into challenge 3. This one is different, so I'd like to explain a few more stuff here. The nested event loops. This is a special structure quite often used in the block layer, because in the bottom of block layer, we implement I/O with asynchronous I/O things. Now we do it like providing two sets of interfaces. One is asynchronous ones, one is synchronous ones. We don't want to duplicate too much, so the nested event loops are invented. This is an example that very well demonstrates this case. We have the AIO cancel here, which is a synchronous version. Don't be confused by the name. And we have a AIO cancel async there, which does the triggering the cancellation, but it's not finished when this function returns. So we need to wait by doing a nested event loop. So the nested event loop would listen for the completion or the cancellation to succeed. Other than cancel, there are a bunch of other examples of where nested event loops are used. Basically, all these interfaces are synchronous, but that hurts. This is an example of where it's actually used in real life. This is a monitor command that does drive backup. It's dispatched in the bottom by the main loop, and later it went into the monitor code to parse the command, and the monitor code would call into the callback of drive backup, and drive backup would start to create the image, whereas the creation of the image is a synchronous operation. So that leads to a correctness problem. I will explain this with an example. This is in the QMP transaction, where you want to back up two disks at the same time without being interrupted by any guest I/O, so that the two backups would be consistent and from exactly the same point of time. So the process goes like this. The first one, okay, even though there is a creation, there is a nested event loop, it's okay. But if this point, after the first one has done, the guest writes to a device, the IO event FD would be notified. The notification will be processed by further nested event loops or top-level event loops, whatever it is. So unfortunately, we still are not done yet. So we have another nested event loop which dispatches the IO event FD event, which means we get a new request that is processed and changes the state of image 2. So the solution is to add an interface to disable and enable around these critical sections of operations. So we want to include the IO event FDs in nested AIO pool. The interface is simple as that: AIO client disable, and we specify what we want to disable. And after we are done, we enable it. So that is in the middle, it's a schema of the QMP transaction. There are multiple operations to do preparation, and when every element of the transaction has succeeded, we will commit it. So what we should do is before we do the actual preparation, we should disable the IO event FD, which is dataplane here. And only after we finish everything, we can re-enable the processing of guest requests. So there are also patches on the list. Unfortunately, we didn't make it into 2.4, but I will make sure that we get this fix quickly. So the solution 3 is this, and that's about it. Any questions?
So I had one question about the part about timers and epoll. I saw that there were some discussion in patches about extending the epoll system call.
Yeah.
But I don't know what happened. Can you kind of explain that and give us a status update, whether there will be a new epoll system call in Linux that supports nanosecond?
Yeah. I think that the necessity of that actually depends on the benchmarking of applications. Because we already have this facility of timer FD, and we can implement the nanosecond precision. So the maintainers would ask for real benefit of a new system call because we are adding more stuff into the kernel. Actually, the current status is that I'm trying to find a real use of that inside the QEMU code base so we can demonstrate whether or not it's necessary.
Okay, thanks.
On one slide, you mentioned that you were considering or preparing to move more code from the main loop into the AIO code. I'm not too familiar with that code, so one thought that crossed my mind was, wasn't the AIO code always optional, so you could turn it actually off in configure? Also, obviously, epoll would not be available on like BSD, macOS, other systems. Is that still being tested, that actually still keeps working when you do the epoll stuff?
The AIO here is the AIO context, which is basically the event loop structure or object of iothread or main loop. And the AIO inside the block layer is how we actually process the request and submit requests inside the block layer. So there are two different things.
So purely a wrapper.
Yeah.
I think you were talking about Linux AIO, not
Yes.
AIO.
Yeah.
My experience says that any sleep will not have a nanoseconds precision. You will stick to milliseconds or even 10 milliseconds. So we have spent a bit of time in previous life, and even if we have to insert timely interrupt into the guest, we do this in advance if we have a gap for 2 or 3 milliseconds. So maybe this never kill. We had just to set the event to happen just 1 millisecond before, something like that.
Do you mean we can run down the timeout? Or?
If you will set timeout in nanoseconds, you will not receive a response. You will not be woken up in nanoseconds precisions. You will be woken up with 10 milliseconds or something like that.
So QEMU does set the timer slide?
If you will set a timer lock, you will not receive event in time, even you will have specified it. Linux kernel is terrible at this thing. It's just maybe my own experience, but it's my feeling.
Okay, thank you.
Going slightly beyond the main topic of your presentation, as far as the event loop goes, sometimes when running Q tests or also under certain conditions running the QEMU process, we've been seeing this warning that Anthony once introduced about the main loop spinning 1,000 iterations or whatever without whatever. At which point exactly does that warning come from, and do you have any idea how we can actually get rid of that?
That warning basically means that we are getting continuous events so that we spin inside the event loop. And we don't yield to the vCPU thread to take the lock and dispatch its PIO or MMO events. So we are concerned that this would hurt the responsiveness of the guest. So we printed a warning there. But in Q-test, I don't think that hurts. If in real applications the warning is printed, I can say that the responsiveness of guest at that point would be done.
Okay, but technically, does that result from the main loop actually processing events, or is that when the timeout kicks in?
I think that's processing events. Okay, so thank you. Thank you for your time.